That'll work just fine. There we go. Okay, linear differential equations. So, we have a differential equation that looks like this. We have a polynomial. I'll do this in both t and x, and then x and y. So in the tx coordinate system, it would look like this. And then we'd have like a function over there. So these are just arbitrary functions of t, and the only x's that appear are as x is the derivative of x and x itself. In xy space, this would look like this. It would be a of x, y prime, plus b of x, y equals c of x. Just to get the rhythm right, notice the independent variable is the thing that is in the coefficients. The dependent variable is the thing that's getting the derivative and the thing that occurs by itself. So let's talk a little bit about why these are called linear to begin with. And we will really get into this. But when you see something called linear in science and math, it's because it obeys this very specific property. So let's just take a look at this part. This is the part that's really linear here. So linear, what does that mean? Well, let's call this, let's pretend this is a function. And really what I mean is this is an operator. So I'm viewing this thing as an operator. So D is an operator. And you will see this later on. We're going to talk a lot about what this means. Viewing this is a very different view of things than we've had so far. So this D is like a function, and it eats another function and spits out a function. So, for example, let me give you an example. If I said D of x is tx dot plus 2x, then I can put a function into this. So I pass a function in. X is a function of t. So if I took d of t squared, well, then that would spit out t times the derivative of t squared, which is 2t, plus 2 times t itself. So here I'm just letting, so x is really just equating with t squared here. And that worked out like way better than I thought it would. But it spits out a new function for t squared. Is that all looking good math-wise and just conceptually? You don't probably know where I'm going with this yet, but as long as that makes sense, you're in good shape. So one way to think about this whole process is, I've got this operator, d of x over here, and I'm trying to figure out what I have to feed it to get that out. This is one really interesting way to look at this. What do I have to feed? What x of t do I feed to d so that when I do this to it, I get that out? So this left side has these really nice properties, and this is where the linearity comes in. So notice that. If I take d of x1 plus x2, each of these is a function of t. Of course, they could be constants, but we think of them as functions of t. If I feed that into this equation, what I get is a of t times the derivative of the sum. So x1 of t plus x2 of t dot, that's on the whole thing there, plus b of t times the x of t, x1 of t plus x2 of t. And then I do this derivative. Now the derivative of a sum is the sum of the derivatives. And that's kind of why this is all going to work out nicely, because the derivative itself is a linear operator. So this becomes a of t, and then we'll just put x1 dot plus x2 dot. And I'm suppressing the of t in that function, but it's still there. this is just x1 plus x2, and now this is just algebra. So this was calculus from here to here. This was the linearity of the derivative. This is just algebra that says this is a of t x1 dot plus b of t x1, that times that plus that times that, plus a of t times x2 dot plus b of t times x2. And notice that this is actually just d of x1. It's the left side evaluated at x1, and it's d of x2 right here. So in other words, d of x1 plus x2 is d of x1 plus d of x2. This is the first essential part of calling something linear. You do it to the sum, and it's the sum of, you've got this process, and you do that to the sum of two things, and it's the same as doing each piece separately, then adding the results. And then also, we could also show that if I take d of some alpha times a function, so this is a constant, then that's just the same thing as first taking d of x and then multiplying that result by alpha. You do this all the time with derivatives. I'm not going to prove it with that because it'll be kind of boring, but if I told you, hey, take the derivative of 3 t to the 1/2, you would first pull the 3 out, and then you would take the derivative of t to the 1/2. That I can do that, that's linearity. That's this part of linearity. So that's where this is, holy shit, there goes that pen. That's where this comes from. Enough of that. We don't even need to know that, but it's good to have this deeper understanding of terms that you're using, and maybe it helps things resonate a little more clearly and deeply. Okay, so before we do that one that I started with, we're going to first look at what's called the homogeneous case. Homogeneous basically usually means there's a 0 somewhere in the process. So, and in here that's going to be the case. So I'm going to have a function of t, x dot, plus b of t x equals 0. And I want to solve this thing. I want to find a function x of t so that when I feed it into this left side, it's annihilated. Have you seen that term annihilator before somewhere? It's great. It's just like a great math term, the annihilator. So this thing annihilates this x, and that's what makes the x a solution. X is a solution if it's annihilated by that thing there. Okay, so first step is we're going to divide through by a of t. So divide by a of t. And here we're going to be careful, like we're going to note where this might be 0 and make sure that any solutions in the future don't cross that boundary. So I'll put a little note here. Note, if a of t equals 0 at some t equals t naught, we'll note that for later. And we'll realize that no t we could ever use in our solution can take on this value because we divided by 0 to do that. And this is something you and I have talked about a lot. All right, so I'm going to do that. I'm going to divide through by a of t, and then the thing's going to look like this. I'm just going to call b of t over a of t p of t, and then the right side's going to be nothing, just that. It's not Q yet. All right, now here's the neat part. This is really cool. I want you to notice that the derivative with respect to t of e to the antiderivative of p of t dt, so this is the antiderivative of p of t, times x, and that's an x of t, equals, how do we do, what rule do I need to do this derivative? Product rule, right? So that's a product of two things. So the derivative of this, let's refresh our memory. d dt of e to the f of x, f of t, is e to the f of t times the derivative of the exponent. So when I do the derivative of this piece, it becomes e to the integral p of t dt times the derivative of that exponent. What's the derivative of that? It's just p of t, right? Because this is the antiderivative. So if I take its derivative, I just get p of t back. Yeah, times x, and then the x is still there. And Chris maybe sees what's going on here. He looks pretty stoked. You look as stoked as I feel about this, so that's a good sign. And then leave this piece alone for the second part of the product rule, times the derivative of that, which is x dot. And let's hold off on that, actually. So in other words, so this looks weird. You might be like, what the hell, why are we doing this? Because it looks more complicated. But if you notice, this is actually just e to the integral p of t dt times p of t x plus x dot. P of t, sorry. That's this. I just wrote it kind of backwards. So this thing here is the same as this left-hand side. Now we're going to go backwards. I'm going to take this equation, so I'm going to call this equation star, and I'm going to multiply both sides of it by something. Luckily, the right side is just 0, so that's sweet. So multiply, so using this observation, let's make some narrative here. Using this observation, this one here, multiply each side of star by e to the integral p of t dt. And then I'm going to do that. So I'm going to get e to the integral p of t dt, x dot plus e to the integral p of t dt, p of t x equals 0 times something. Okay. I'm going to let you get caught up. There's a lot of writing, fast talking, fast writing. So that left-hand side actually is just this. Yes, Kendra?
So was this, did we use E just for the example, just to show that it's equal, or is there significant?
It's significant, because the key thing is that when I took the derivative of this, that's what got that p of t out inside there.
So is it equal to anything in the equation, or is it equal to the entire equation?
Hold on, let me finish this, and maybe this will make sense. Let's talk right after this moment.
Okay.
So this left-hand side, just for all I need you to agree with is that this, work backwards, is this. The left-hand side is this now. So to convince yourself of that, and if not, let's talk about it. But the left side is actually just the derivative of e to the p of t, integral p of t dt, x of t. And I'll put the little x of t in there to make that clear. So that is a very special value, Kitra, and no other thing would have gotten, there's nothing else I can multiply through by that would have the same effect of when I take its derivative, the p of t pops down, and then it also just rides along with the x of t when I take its derivative. There's just no other function that would do what we're trying to do here.
I don't know if I'm just confused. I don't
No,
understand
ask,
how it relates
please.
back to the original, like the one above.
Like
what you said.
this?
Yeah.
Okay. It's literally just a multiple of this. So notice that this left-hand side, I'm glad you're asking. So this left-hand side is e to the integral p of t dt times the original equation that we had. So I took my original equation, multiplied it by this, and then it becomes writable like this. Maybe that's a good way to see it. we're gonna get a nice step-by-step process. But look at what's going on here. If I just integrate each side with respect to t now, so this left side, so we're gonna integrate with respect to t, the left side just becomes undone. And the right side becomes a constant. That's just an integration constant. And so my solution is I just multiply by e to the negative integral p of t. So x of t itself is c e to the negative integral p of t dt. And here's our solution. We got a formula for it now. So what the whole purpose of this was to actually derive that form of that solution. Let me give you a second, and then let's test it out together. Let's take this for a drive before we, you know, soup up things a bit. So for example, solve x dot plus 1 over, well, let's just do t. dt, tx equals 0, good lord. So I want to solve this. First thing I do is I recognize that it's in this form of a linear equation. So I note that it's this form here. Yeah, got that form, so we're good to go. The first thing you would do if you had this form would be to divide through by that leading coefficient. So you want to be able to get it to look like that. And we've got that. We're just given that. So this thing I'm going to create is my integrating factor. So this integrating factor is going, and this is p of t right here, is going to be e to the integral p of t dt. And that's equal to e to the integral of t dt, so that's e to the 1/2 t squared. And let me kind of walk through with this whole thing so you can see it. Like I'll kind of do the proof again, but instead of just jumping to the formula, which I could do right now, let's think about how this thing works. So you take this integrating factor and multiply, and this might help too, Kitra. I'm going to multiply this equation by that quantity. So on the left side, I'm going to get e to the 1/2 t squared times x dot plus e to the 1/2 t squared times t times x equals 0. You're not going to do this in general. In general, you're going to go straight to that form down there, but I just want to let you see this another way. Notice how beautiful that is. This left side is now this. Check that out and convince yourself, like, believe this. Yes, Hans?
So I might have missed it earlier, but is the e, is that coming from like the function itself, or is that just like a magic sort of like tool that we have?
It's a magic tool.
Okay.
Yes. And I'm trying to motivate why it works. You know, like, and you're going to see it here. Like, check this out. Take the derivative of this left-hand side. You get e to the 1/2 t squared times x dot, plus take the derivative of this. That derivative of this gets you that t here. That was the point. It gave me that t. And I still got this thing in here. It doesn't matter. Notice that this thing here, this e to whatever, this can never equal 0. Because it's e to a power. It can never equal 0, so I'm never dividing by 0 or doing something crazy like taking this equation and multiplying both sides by 0 to make me think that was okay. Right? Because we can do multiplying by 0, it's a powerful thing, also a dangerous thing. So this, now integrate both sides, you get with respect to t. And so x of t is ce to the negative 1/2 t squared. And let's check that out. Let's just verify that. Let's do all sorts of freaking verification. So, to To test this, to see if this is my solution, I'm just going to take x dot. So x dot is going to be negative 1/2 c e to the negative, well, let me slow down. It's going to be c e to the negative 1/2 t squared times the derivative of the exponent, negative t. And x itself is this. So when I plug this into this expression, take x dot plus t times x, can you see that I'm going to get c e to the negative 1/2 t squared times negative t for this, and then just plus t times c e to the negative 1/2 t squared here, and then they just cancel. I get 0, and it works. Let me give you one to try. Before we, like I said, soup it up. Oh gosh. All right, so here's a good one for you. We're gonna fix this. So I'm gonna start off like this. I've got t x dot plus x equals 0. But remember what we want. We want to get it into this form to use this integrating factor thing. So I divide through by t. So to get into I divide through by t, and I get x dot plus 1 over t x equals 0. Find your integrating constant. Yeah, let's all find the integrating factor first. So e to the integral p of t dt. See any absolute values, toss them out the window. You'll be so much happier if you get rid of the absolute value.
I'm kind of behind, but
That's okay.
so like up there you have like the e to the 1/2 t squared.
Yeah.
And like I guess so then you're able to go from like the like this to the d over dt.
Yes.
Okay.
Yes. So like in
I
the
see.
end, yeah. So in the end, what you're going to be doing is a rewrite of the left side as d dt integrating factor times x.
Actually, yeah, I guess yeah, I remember that.
What is my integrating factor here? Yes. Yes. T. With less of a question added to it. But yes, so let's do this. My integrating factor is e to the integral of 1 over t dt. And then that's e to the natural log of t. We put the absolute values there, right? Usually, just to be safe. And so remember this, those undo each other. So it's just absolute value of t, and then someone, I'd like to think wise, said toss those out the window. So what happens when I multiply the left side by t? I just get back the original, right? Let's do it. That's basically telling me this thing was perfect to write as ddt of a product of two things. So let's go through, then we multiply by t on each side, my integrating factor, bless you, and I get tx dot plus x equals 0. But really, what I was trying to go for was this. It's the derivative of t times x. Notice that the derivative of this is our original equation. Check that out. Convince yourself of that. Does this seem clear? Derivative of this is my original equation. That's what the integrating factor was telling me, like, oh, this thing was perfect to begin with. That's great. So, the solution is now integrate both sides with respect to t. That becomes a constant. So x is c over t. And then if we had initial conditions, we would rock out c at this point. Let me stop. Can you solve that problem in a different way? Let's just see. Take a moment. Solve that problem using a different method to make sure that this is all legit. You know two other methods, so it's one of those two. Maybe both of them. And then we'll lay out an algorithm for those who like step-by-step procedures. I think it's separable, right? Seems pretty dang separable. I don't know that it's exact though. Something tells me not, but maybe. Oh, it's exact also. That's pretty cool. Yeah, what do you know? Yeah, I think so, right? So, yeah, sucker's exact. I'll do it the exact way. Let's see, so it's exact and it's separable and it's linear. That's exciting. I feel like one of the exam problems will be like, I'll give you a simple problem and ask you to solve it 2 different ways. Something like that. And it'll be solvable by 3 different ways. So you got lots of room for being right. So let's see here. So what do? We usually go partial of f with respect to x is this thing here. So I integrate up. F becomes, oh wait, easy buddy. There we go. Tx plus a constant with respect to t, and then I differentiate down, so now I take partial of f with respect to t, and I get x plus c prime of t. C prime of t is 0. There's none. So c prime of t equals 0. And then my final equation must just be this. F is equal to tx. And so my solution is tx equals a constant. Pretty much exactly what we have. Did separation work out the same way? Did we do, let's do it with separations. So with separation, we've got t dx dt equals x, negative x. Right? And so that's, oh gosh, what a pain. Move the dt over, so it's dt over t equals dx over x, and I think there's a negative in there, right? Is that looking okay? Does it look legit? Yeah. And then do both sides, so it's natural log of x.
dx over negative x.
I'm sorry, say that again.
I think it's dx over negative x.
Oh, I think that's okay. It's okay. That's totally cool too. As long as we got that negative in there somewhere, Nathan, we're golden. So, yeah, but I appreciate you watching and keeping an eye on me. So this is negative natural log of t plus c there. Let's convince ourselves that these are the same, because that does not look like those two, right? We got to do a little work. Take the exponential of both sides. So you've got e to the log x equals e to the negative log of t plus c. And we know this e to the c thing, that'll just become our constant out in front. and then this becomes x. And then this, notice that this is actually c over e to the natural log of t. So that's c over t. Toss away our absolute values. It's the same thing. So it's really, I think it's really fun and cool when it can be solved like by everything we've ever done. It's just really lovely. And trying to make them reconcile is another fun part of it. Is there anything here you'd like to talk about? And that, it's kind of a little bit of review too. So, to solve the non-homogeneous problem. There's a lot of descriptors here. To solve the non-homogeneous linear first order differential equation, a of t x dot plus b of t, I was thinking, oh, I should be doing this in y, equals c of t. Step one, get into form x dot plus p of x, p of t, x equals q of t, divide by this leading coefficient, or y prime plus p of x, y equals q of x, if we're doing the x, y scene. That's step one. Step two is find your integrating factor. And your integrating factor is going to be e to the integral of p of whatever dt. So in this case, it's going to be that, or in the other case, it's going to be this. Now, the reason for doing that was so that when we multiplied through by it, the left-hand side becomes an exact derivative of a product. So there's this exactness kind of coming in here. The term exact fits perfectly here. So step three is, you don't really have to do this, but I'm going to write it out here, and then we're going to put it to practice together. Multiply each side by this integrating factor from this step. The left-hand side becomes d dt of your integrating factor times x, or it's d dx of your integrating factor times y, depending on what land we're living in. The left side just becomes q of t times your integrating factor. Did I say left? I meant right. I don't know what I said there. I meant the right side. The right side, RHS, right-hand side, becomes integrating factor times q of t. So we'll have this. And you can just go ahead and write this if you want. Your integrating factor whatever that q was here at this point. Now integrate both sides with respect to t. And this is where the work will really come in. This is where we actually have to maybe do some nasty integration on that right side. So then step 4 is integrate. We're actually going to come up with a formula here that you can absolutely use instead of doing all this. Integrate each side. The left side becomes this beautiful that. The right side becomes something that looks very integrally. There's lots of integrals going on that right side. We'll tack on a plus c while we're there. And then I multiply through by the reciprocal of this, the integrating factor. So my final solution, 5, is isolate x of t, and this is one of those cases where the explicit solution is what we get. This is the kind of shit you show your friends, right? Like, this is good, this looks good. Looks like you're really doing something. Like double integrals and all that stuff, that's awesome. So this is the general solution to that problem. If we have a specific, yeah, exactly. If we have, you can just write that down and use that, nothing wrong with that. You still gotta do the calculus. So let's do one together. Might have some like cool ones in my notes. I hope I have some cool ones in my notes. I've let myself down terribly if I don't. Come on, pass Timmy. You can do it. He did it. Pass Timmy, pass Timmy. All right. Good boy. So, solve. Y prime equals 1 plus 3y tangent of x. We'll have a little bit of a challenge here. So, instantly I'm going to a form that I didn't lay out the outline in, but that's okay. Step 1 is to get it into the right form. Well, I guess that's step 0, kind of. So I'm going to rewrite this as y prime minus 3 tan x y equals 1. So I want, the rhythm is this. You've got something y prime plus something y equals whatever else is left. Little wolf face. Cool. So I've got that. Now I isolate this, or just grab this part and create my integrating factor. My integrating factor is going to be e to the integral of the coefficient of the y. I don't need to divide by anything, right? I've got a 1 here. So this 1 came with a 1 out in front, so we don't have to like divide through by anything. So my integrating factor is going to be e to the integral of negative 3 tan x dx. Let me give you a moment to chill with that integral. See how that goes.
dx or dt?
Oh, thank you. Yeah, that should be dx. Good call. Good call. Got myself all worked up.
I actually said dx, but you wrote
I appreciate you keeping me keeping things straight for everybody. And then see if you can get it down to something that doesn't involve e at all. Because you can. The integrating factor will not look like an exponential. Let me come around and see how things are going. Olivia, where are you, my friend? You're not over here. I came to talk to you. I'm sorry, I'm just talking to Olivia in the recording. So. Doing good? So how'd you get, okay, so that, you might need to look this up if you haven't done it in a while, what the antiderivative of tangent is. Yeah, that's cool. So,
That's weird.
So there's like that table that I gave you guys. I would have like a copy of that somewhere, you know, some kind, like, you need it, it's like your driver's license in this class, right? Like, you don't wanna get pulled over by me without having an integral table. So, let's talk about that integral. Can someone help me with just, how would I do this if I didn't have a table?
Switch it to sine of x or cosine of x.
Like that. Then
U sub.
U sub. So let's talk about U sub. When you have a fraction and you need to sub, and you don't see parentheses, this is probably what you have, a natural log form. In fact, in this class, natural logs are all over the place. So this thing here, I'm going to let u equal cos x, du is negative sine of x dx. And then I would solve this for dx. I'd get negative du over sine of x. And when I do the rewrite, I get negative integral du over u. Does this look okay? Look reasonable? Check it out. Make sure you're with me. And if you're not, tell me, and we'll talk about it. Good? Yeah? And I would just not incorporate, don't do the plus C when you're doing these integrating factors. Does that look, let's take a look. Distract. I don't know if that helps. How does this look? Tell me if it's right, for one. Like, I'm also like asking, am I doing it right? Because you all have like good eyes and catch me on lots of stuff. How do I undo that? Hans, yeah.
I think it's actually secant. Natural log of secant.
Yeah.
I agree. That's the same thing. So check this out. This is negative natural log, u is cosine, yeah? That?
Oh, the exponent.
That comes up as an exponent,
Stupid shit.
and that's secant. It's 1 over cos. So good, yeah, you're absolutely right. It is secant. These are great questions because we get to talk about all this stuff. Very exciting. At least I seem pretty excited. I'm not sure anyone else is seeming super excited. So do you see how the negative, there was like this -3 here, and I just canceled that with this negative that was existing there, so it became a +3. Let's make sure everybody's up to here. How do I undo, what's my next step? I said I could get this with no e's and stuff. What's the next thing I need to do? Move the 3 as to an exponent. Because the only thing you know how to do is this. And if there's something out in front, it's got to all be in here. So it all has to be in this exponent with the log. So this becomes e to the natural log of cos cubed. Let's just issue the absolute values. I don't know if that's the right word there. This isn't an English class. Fuck it. We don't need them. So to say it a little more crudely, quite crudely, we've got this, and so my integrating factor is somewhat mysteriously cosine cubed. That's wild. But let's convince ourselves that that's actually gonna be okay. But up until, let me wait, because I would like to make sure everybody's cool with this. I've been hearing rumors like people saying diffie-q is hard. It is. You're right. because of like all the stuff, all the things you have to know, right? Like literally all your math knowledge comes back to not hopefully help you, not harm you. Okay, so let's multiply through by this, and it's gonna look weird for a minute. So I'm gonna take this form right here, I'm gonna call this star. I'm gonna multiply star by my integrating factor, and what I'm gonna get is cosine cubed of x y prime minus 3 tangent of x cosine cubed of x y equals cosine cubed. Are you kidding me? What's going on? That doesn't look helpful. Notice that tangent is sine over cosine as well, right? So this tangent is sine of x over cosine of x. So let's rewrite this. So this is cos cubed of x y prime minus 3. One of the cosines cancels. I'm left with 2 of them times the sine of x. I'll put those of x, and that's a y equals cosine cubed x. And notice that the left side is just d dx of cosine cubed of xy. Notice how pretty the left side turned out, right? Because you got to do chain rule on this. This cosine cubed goes to 3 cosine squared times the derivative of the inside. That's where this came from, right here. All hidden quite nicely. You don't need to do this every time. Friends, all you need to do is identify this, that integrating factor, and then go to this part. X of t is going to equal e to the negative, oh wait, oh no, this is, what was that form that I had here? E to the negative, just to make sure, let me make sure this is right. Shit, let me do it in x's and y's. So we had y equaled e to the, so we had integrating factor, inverse, times, God, I have to write the whole damn thing out. Now I don't even remember what the formula was. So it was y equals e to the negative integral p of x dx times integral, oh yeah, okay. E of integral x times p q of x, yeah. Yeah, okay, bless you. It's easier to just actually think this all through. I think that actually might not be the worst plan for a while. To try to understand, instead of just going to that formula, understand what you're doing. Seems like a more useful thing. Integrate with respect to x. Left side's easy. We built it to be easy. How do I do that integral? Anybody remember? This is not trivial. We could look it up. It's in that table. There's actually a cosine cubed formula in there. That would be really sweet. So that's one answer. But how would you, let's just talk, because it's so much better to understand how to do things than to look them up, right? So, oh, yes, Anthony.
Or it's like, can we rewrite cosine squared as like sine squared plus 1?
There you go. Yeah, all right. Yes, absolutely. So then this, I rewrite as 1 minus sine squared, trig identity, because sine squared of something plus cosine squared of something equals 1. This is like, you got it, that's like everywhere in the world. The world cannot move without that identity. And then, so I get this, I rewrite cosine squared as this, and then this just becomes 2 integrals. One is easy. The other one requires substitution. That times that, that times that. Here I would let u equal sine, then du would be cosine. So in this part right here, this just becomes sine of x. This becomes, so think about this, this is actually a u squared form. It's this. So it's 1/3 sine cubed of x plus c. Or look it up in the table. I don't care how you get these things done. This isn't a calculus class, so I'm not going to check to make sure you know how to do parts and substitution. I don't care how you get your integrals done as long as it's not with a calculator. Because we have to be ready for when everything goes to hell. We've got to be ready for when the power goes down, the grid is down. You guys, we're gonna rebuild shit. And you don't rebuild it without knowing something that is very integral-ish. All right, so this is cosine cubed. So this is where the work comes in. The rest of this is like a game, right? You just follow the flow. Then here you're like, oh shit, I actually have to know how to integrate that. And that's okay. Tack on the plus c, multiply through by the reciprocal of this thing, so y equals sine of x over cosine cubed of x minus 1/3, oh hell, I'll just call it tangent cubed of x plus c, and then let's go for some of that secant action somebody was mentioning earlier. Secant cubed of x. That's 1 over cosine cubed of x. You don't guess that. You do not guess an answer like that. It's really atrocious looking. But that's it. That's why DiffyQ is hard, right? Let's do more. More! I hear you clamoring. I have a good fantasy life, so I can imagine all sorts of things. Go home and tell Amy, they wouldn't stop begging me for more problems. Oh, how about a nice one? Would you like a nice one? Yes? I don't know if I have one. Okay, I'm trying to find one. Let me go back. Maybe earlier in the notes there was something pleasant. Yeah. Okay, here we go. Please solve. X dot plus 2x equals t. See, I left you with the nicer thing to do. Step 1, integrating factor. What is your integrating factor going to be? Let's make sure. Let's get that and check in together. Hurt your hand, Libby? Did you fall?
No.
Maybe you don't want to talk about it either, so I shouldn't. be
No.
worried.
I usually just woke up from sleeping at.
And it must have some crazy dreams. Yeah. Wow. I do that too.
Yeah.
Yeah, I like hurt myself during the night. You wake up, it's like, what happened? The wrist one, though, that's pretty intense. What's my integrating factor? What is it? What do you think it is? Anybody got an integrating factor for me? You can do that, you can look at that, and do it in your head. Yes, Thomas.
Is it e to the 2t?
It is e to the 2t. It's e to the integral of that coefficient right there. Yeah. So here the integrating factor is just e to the integral of 2 dt, and that's just e to the 2t. And that's not bad, right? Yeah, Lavina, yes.
Oh, no. Yeah, I realized something, okay?
Is it? You're okay?
Yeah.
Okay, good. Let's do this the fast way. So now, once you get good at this and you understand what's happening, this left-hand side now becomes d dt of the integrating factor times x. And the right side becomes the right side times the integrating factor. How pretty that is. Can you take this home? And then let's incorporate a nice simple initial condition too. Get the C, do the whole thing. How this looks like. Person who's got this all locked up. No, okay, you just, well, you have a look of confidence, so never give that up.
Okay.
Yeah.
Confident. I'm
Yeah,
gonna be
exactly,
honest.
it's good, no,
Whenever
like,
I look confused.
being able to bluff your way through anything.
Dr. T.
Yes. Let me come take a look. Yes, Hans.
So I'm just confused. How do you get this inside the brackets?
That's like what that whole, that's what, so like check this, do it backwards. Derivative of e to the 2t would be e to the 2t times 2 times x plus e to the 2t left alone times x dot. That's this left side with just that e to the 2t times it. So notice that that derivative of that thing is actually this left-hand side if you multiply it by e to the 2t.
Okay. So it'll always just be
Yes.
the integrating factor times
As always, that was why that's how we built that integrating factor too, so that this left side always becomes this. The derivative of the integrating factor times the dependent variable. Yeah? Yeah.
I got some pretty got this a lot.
Yeah, integration by parts now is your friend, which we'll review in just a second.
Okay,
That's the UDV. That's the yeah?
Okay. Okay.
So things like when I say, talk about integration by parts, if that sounds distant and hazy, you might want to go check out a couple of my Calc 2 lectures from this semester. I can actually, if you send me an email, I'll send you right to the ones you want to watch. It's probably only 2 you really need to check out. Maybe one will get you going real fast. But it kind of goes like the way my classes go. I'll talk and then you can work problems with me and then you'll find out how you did. And let's talk about the fast way to do integration by parts. So let's do tabular integration. It works with any level of integration you want. The basic idea is that if you have this integral that looks like this, you can rewrite it like this. This is the key formula from integration by parts, which is actually just the reverse of the product rule. I don't want to get into that, but that's what that is. If you move this to the other side, it's the product rule. But here is a nice way to do it. So this is called tabular integration. And it's just, you don't have to worry about all this stuff. So here we keep track of the sign, because there's this sign change every time we do a level of integration. This is the thing I'm going to differentiate, and this is the thing I'm going to integrate. I always initialize this table with a plus. And then here, I put the part of the integral. So notice how it's a product. This is a times in here. right? I say times, there's multiplication. This thing is the part that gets simpler when I differentiate it. So that's gonna be t, because then that goes to 1, and then that goes to 0. Over here, I put everything else. This is probably one of the most useful laws of integration in existence. That's just like a substitution. I would know that, like, just have that ready. You're gonna do that a billion times in this class, and a billion times in any science class. So this, so now that I take the center column and I differentiate down until I get 0. T goes to 1, 1 goes to 0. Propagate this alternating signs, plus, minus, and then integrate here. So this goes to 1/2 e to the 2t's, and got k equals 2. 1/4 e to the 2t, because there's already a 1/2 up front. So then, the pattern is this. Go across and down and multiply. Across and down. So this becomes plus 1/2 t e to the 2t. This becomes minus 1/4 e to the 2t. Add these together and you got your answer. So 1/2 t e to the 2t minus 1/4 e to the 2t. That's our right-hand side. That's how I'd do it. I used to just save that for repeated parts, but there's something just cool about just using it for normal parts, just like a singular part. And then, so this now, I'll check in on you in a minute. This becomes e to the 2tx equals 1/2 t e to the 2t minus 1/4 e to the 2t. And something really beautiful is going to happen here when I tack on the plus c. Notice that when I finally isolate the x, look at what happens. This cancels. And I get 1/2 t minus 1/4 plus c e to the 2t. There is my general solution. Those e to the 2t's canceled out, Thomas, yes.
Or would it be like e or c e to the negative 2t?
It would, thank you. Yes, it would. Good call. Thanks. And then we do our initial condition when t equals 0. Oh man, it's not pretty. Okay, so let's do the initial condition and call it. This will be it for today. We are going to let x equal 1 and t equals 0. And so then we get what? 1 equals 1/2 times 0 plus that quarter's the part that's making me cringe a little bit. Plus c e to the negative to 0. So that's, oh, that's not so bad. Oh no, I don't know what, yeah, I just diluted. So that's just 5/4 equals c. Not bad. Oh, that's pretty. Then we put it all together, and we get x equals 1/2 t. And I want to talk about this solution too before we go today. So there's my beautiful, complete, particular solution. I want to show you how to graph that if you don't have a calculator, because we're all about like rebuilding society, right? Like from coconuts and shit. So let's talk about how you would graph this without a calculator, like really nicely graph this. First off, notice there's two parts. There's like this part, which is a line, and this part, which is an exponential function. So e to a negative power looks like this, and e to the negative 2t could quite well look like that. You should kind of have a sense, I think it's good to know what e to the x looks like, what e to the negative x looks like. It looks about like that. So this piece out here is dying off as t gets bigger. This is persistent. So this is like transient, to use a science word. This is a transient piece right here that dies out as time moves on. And all we're left with is really this in the end. So to sketch this thing out, I'm gonna sketch this line first, 1/2 t minus 1/4. So that's a line with a y-intercept of -1/4, slope of 1/2, so when t equals 0, I'm at -1/4, when t equals 1, I'm at 1/4. So there's 1/4, there's 1/4. So this line right here kind of acts like an asymptote. And then I add this e to the -2t on top of it. Let's see, that would add 5/4 to the -1/4, so this should go through 1, right? That was the initial condition, and it does. And then when you add this thing on here, what you see is that it's approaching this line as you come out this way. And it gets closer and closer to that line, so something like that. So at least you have some sense of how, its behavior is. This isn't asymptotic here, this keeps on cruising, so maybe. Okay, that's all. That's all I wanted to tell you. You got out early today. Congratulations and thanks. And there's a web work that's opening up because why not continue to hammer you with work? And it's probably like says it's due Thursday, that's a lie. That sounds way too soon. So first things first, we have an assignment due on Wednesday, right? Bring your laptops to class on Wednesday. I don't think that sounds like the worst plan. We might do some work together. Thanks, friends.
Thank you.
Thank you.
You put my notebook inside.
Is it listening to you now? Does it acquiesce?
Yes,
Okay.
actually, after I asked it, hello.
Who's in there? Okay.
I think I need to go back to tab 1 again. Tab 2 again. Like now that I'm like going back and doing all these different types of like I've definitely done tabular integration before, but I think it was like I literally did it last semester. I did it freshman year. Oh, so it's been a minute. I really hope this isn't recording. It's gonna be super embarrassing. Yep, it is.